Today I'm going to talk about complex numbers and I'm going to do some calculations with them. The first calculation I'm going to do is I to the power of I to the power of I. We can use Euler's equation to write that out. We can say this equals cosine pi over 2 plus I sine pi over 2 to the power of I. We can see that that is correct because cosine pi over 2 equals 0, sine pi over 2 equals 1, so indeed this is y to the power of y. And this can be written as, with Euler's formula, e to the power of I pi over 2 to the I, which is then I times I is minus 1, which is then e to the power of minus pi over 2. What we calculated here is just the primary branch. In complex numbers there are way more solutions to this. It's not a single valued function, it's a multiple valued function. And we can see that by going into a slightly different way of evaluating this. And we are going to use the following formula for that. If you have z to the a, where z is a complex number and a could also be a complex number, this is equal to e to the power of a log z. Where log is not just covering the primary branch but all branches of the solution. So if we write this out, we get e a log c absolute, and note that this is a capital because it's all the branches and this is just a primary branch, and I note that with a small cap, plus I arc z, so the argument of the z, so what the angle is, plus I 2 pi k, where k is an element of z. And in this case you can see that there are multiple solutions to z to the power of a, not just one single solution. There's an infinite amount of solutions because of the branches. So if we use this formula for I to the I, we get I to the I equals e to the I, then we do log I absolute, plus I, the argument of I, which is pi over 2, plus I 2 pi k, and this equals the log of I absolute is the log of 1, which is 0, and you get again e to the power minus pi over 2, because this is 0, this is pi over 2 times I squared, which is minus 1, that's that one, and then again you get minus 2 pi k with k element for z. And now you can see that I to the I doesn't have a single value as a solution, but it has multiple values as a solution, and they're all valid. Yeah, that's the interesting part about complex numbers versus real numbers, where you have single valued functions. If you do 2 to the power of 3, there's only one answer, and it's not a whole range of answers. With I to the power of I, that is not the case. Let's do something different. Let's try to evaluate sine I. How are we going to do that? Again, we're going to use Euler's formula, and as a side note, let me evaluate that here. E to the power I alpha equals cosine alpha plus I sine alpha. Yeah, that's Euler's formula. We can also use that with a minus alpha, and then we get again cosine alpha, because cosine minus alpha equals cosine alpha, because it's an even function, minus I sine alpha, because sine alpha is an odd function, so you get a minus. You subtract those, you get I alpha minus I alpha equals cosine minus cosine is 0, I sine alpha minus I sine alpha is 2I sine alpha, and the result is that sine alpha equals EI alpha minus I minus I alpha divided by 2I. And that's the formula we're going to use to evaluate this one. So we can write this out. We can go back and say, okay, what is sine I? Sine I is then I to the I. Alpha is in this case I times I, right? Minus I times I, yeah, divided by 2I. And that gives you I minus 1 minus I, or E, sorry, E minus 1 minus E, divided by 2I. And that's the value of the primary branch, again, of sine I. And if you look carefully, there are complex values of C you can take such that sine Z is bigger than 1. That's possible. Yeah. And in fact, the example just given is in fact bigger than 1 in its amplitude. It's about 1.17 if you check that on your calculator. So I think this is a good place to stop. If you like this video, please like and subscribe. See you next time.